This is lesson 8.6 on vectors. So we're going to do a little bit of work with them. Starting with this warm-up problem. Find the magnitude of a vector with an initial point 1, 2 and a terminal point 7, 4. So if we want to find the magnitude, the first thing that we're going to do is we're going to plot the starting location and the finishing location of our vector. Okay? The vectors are drawn like rays, so I've described it like a ray, though I put ray in quotation marks because a vector has a specific stopping point, and rays don't do that. Rays move in a particular direction indefinitely. But vectors do have a specific length, and that's what we're trying to find here, the magnitude or length of this particular vector. Okay? So what we need to do this, and this may look familiar, and you may remember from finding the distance between 2 points, this is just the same. We want to figure out how far we're moving in the x direction, which is 6, and how far we're moving in the y direction, which is 2, and then find the magnitude or length of then that what is now the hypotenuse of our triangle. We could use the distance formula with these coordinates instead, but I've always recommended that the Pythagorean theorem works just as well and is usually a little easier to remember. And so we've got 6 squared plus 2 squared will equal the magnitude of our vector squared. 6 squared is 36 plus 2 squared is 4 equals the magnitude squared. So 40 will equal to the magnitude squared of our vector. Taking the square root of both sides, we'll find that our vector's magnitude is the square root of 40. And simplifying, the square root of 40 is the square root of 4 times the square root of 10, or 2 times the square root of 10. And so the magnitude or length of our vector is 2 times the square root of 10. So I've just told you one component part of a vector. A vector is a representation of a magnitude. Magnitude represents how far something is going to move. Okay? But not only that, the coordinates that I gave you for our vector also specified a particular direction. And this encompasses the definition of a vector. A vector is a way to represent a direction of movement and a length of how far that movement is going to be, and that we refer to as the magnitude of the vector. Let's talk about a couple more parts. First of all, component form of a vector. Okay. The component form of a vector is written much like a coordinate is. Okay. Rather than parentheses, we use these kind of angle-shaped brackets, but we're still going to put the vector into an xy form. In this case, the number we put in for x represents the change in the x direction. How far did it move, our vector, in the x direction? And did it move to the left? Did it move to the right? And then the y is going to represent how much we change in the y direction. So if we are given a vector, -3, 7, that means we move left 3 in the x direction. So let's say we start at the origin. We could start anywhere on the graph. It moves left 3 spaces and up 7 spaces, a change of 7 in the y direction. Okay? And our vector has a specified direction. That's a pretty terrible line. Something like that. Okay? And this is our vector -3, 7. And we could find the component form of the vector from the warm-up. Started at 1, 2 and ended at 7, 4. 1, 2 is here, and 7, 4 is here. And we talked about in the warm-up how our x changed +6 and our y changed +2. So this written in component form would be 6, 2, saying that it moved 6 in the x direction and 2 in the y direction. Okay. Now notice the vector notation has nothing to do with where you start on the graph. It only tells you how far and in what direction you move. Okay. Component form is not the only way to talk about the direction and magnitude of a vector. We can also talk about the direction of a vector using degrees. Okay, so let's take a given vector. Let's say we have our vector. Let's stick with the one from the original problem, 6, 2. Okay. That means we start at any location on our graph. We move 6 in the x direction, 2 in the y direction. Notice that I've changed this to be starting from the origin, and that's okay. We found in the warm-up the magnitude of this vector. The magnitude is equal to 2 times the square root of 10. That means the length of this is 2 times the square root of 10. But what direction is it going? Okay. Well, direction of a vector is measured by figuring out the angle measurement needed to move the vector from the x-axis clockwise to the current location of the vector. So what we mean is we want to find this angle measurement right here. I used a theta to represent the angle measurement. So we're trying to figure out what theta is. Okay? And this is why vectors are taught in this chapter, because finding theta is going to require some trigonometry. All right, I've blown up our vector here. So here's our vector of length 2 times the square root of 10. We know that this side length is 2 and this side length is 6, and we're trying to figure out what this angle is. Well, we could use any of our trig functions, but sticking to whole numbers, let's use tan. The tangent of that angle measurement is going to be equal to 2 divided by 6. And that means that our angle measurement is going to be equal to the inverse of tangent, or arctan, same thing, of 2 over 6, or 1/3. And typing that into a calculator, we find that the inverse tan of 1/3 is equal to 18.435 degrees. So another way we could talk about our vector is that we have a vector in a direction of 30 degrees with a magnitude of 2 times the square root of 10. And that would tell us exactly what direction and how far you need to travel. Write a vector with a magnitude 12 and direction 30 degrees in component form. Okay, so a direction of 30 degrees, direction is always measured clockwise from a horizontal line. Okay, so if we've got a direction of 30 degrees, that means we start at the horizontal line and we move 30 degrees in this direction. Okay? And so if we do that, we get a vector that would look something like this, and this angle measurement would be a 30-degree angle. Okay? Our vector's magnitude is 12, and we want to know its component form. Well, to write it in component form, we need to be able to write it with the x and y components, or how much does it change in the x direction and in the y direction. And again, we're going to find what we've learned with our trig functions is going to be helpful. If we drop this line, we create our right triangle, and our y component is going to be that length, and our x component is going to be this length. Okay. Set up a couple of trig functions. The sine of angle 30 will equal y over 12, and the cosine of angle 30 degrees will equal x over 12. In fact, we don't really need sine and cosine. We could use our 30, 60, 90 triangle properties. Okay? And if we do that, we're going to find that angle y is going to equal 12 times the sine of 30. And you could type that into your calculator, or you could remember that the side opposite the 30-degree angle is in fact equal to half of the hypotenuse. So that component's going to be 6. Our x direction is going to be 12 times cosine of angle 30, and we could type that into the calculator and get a decimal version of it, or we could remember that in a 30, 60, 90 triangle that the 60-degree side, the opposite of 60 degrees, is the 30-degree side times the square root of 3. So 6 times the square root of 3. And so the component form of our vector is going to be 6 times the square root of 3, comma, 6. Okay? And we have two different ways now to write this vector. This vector has a magnitude of 12 and a 30-degree direction, or it has a component form of 6 square roots of 3, comma 6. Let's do one last question. Find the magnitude of a vector with x component 6, y component -2, and find the direction of that vector. All right, so let's start here. Let's start at the origin. Component vector tells us to go right 6 and down 2, giving us this vector right here. Now if we want to know the magnitude, this is a fairly similar problem to before. We would do 6 squared plus -2 squared equals our magnitude squared. Again, doing the x side of our triangle squared plus the y component side of our triangle. And that's again going to be 40, and we've already done this problem. The magnitude is 2 times the square root of 10. Now for the direction, we need to remember that direction is measured counterclockwise starting at the horizontal. So we need to know how far to move around this circle. Now we know that an entire circle is 360 degrees. So if we know this angle measurement right here, we could subtract that from 360 degrees and figure out what the entire angle is. All right? Well, we can figure that out. We've got our triangle here. Got an x component of 6 and y component of -2, or a side length of 2. And we want to know this angle measurement right here. So tan of this angle is equal to 2/6. We could actually use a -2 if we wanted to indicate direction, and we're going to find that we'll get the same answer. We'll get the same angle measurements, which would be great. So that means I need to, in order to find that angle, do the arctan, or inverse tan, of -1/3. And if we do that, we're going to find that our angle measurement is 18.4349, so on. But we got to remember, we measure in counterclockwise direction, so if we subtract that from 360 degrees, we'll find that the direction of our vector is 341.57 degrees. That's our direction. This is our magnitude of the vector.